Today we'll learn how to solve all kinds of exponential and logarithmic equations. You actually already know how to do much of this, so what I suggest is that you take your notes, do one problem with me, and then try the others on your own, checking your work, fast forwarding through the stuff that you can do quickly. So here we go. With exponential functions where we can get like bases, you get those like bases and then you set the exponents equal to each other and solve. These are always no calculator problems. So these would always show up on a part 1 of my quiz or test. So let's do some examples. In example 1, I have 3 to the x equals 9. Well, you know that 3 squared equals 9. But just to understand the process, we would rewrite this as 3 to the x equals 3 squared. Now that I have equal bases, then I can drop those bases, set the exponents equal to each other. X is equal to 2. In example 2, I have 2 to the x plus 2 equals 8 to the x minus 2. Well, 2 to the x plus 2 will stay put. 8 can be rewritten as 2 cubed, and that's all to the x minus 2. Use our power to a power rule, and we get 2 to the x plus 2 equals 2 to the 3x minus 6, distributing that through. Now that you have like bases, set your exponents equal to each other and solve. So we have 2x equals 8, x is equal to 4. In example 3, I have 0.1 to the negative x equals 10 to the 2x plus 1. So anytime you see a decimal, you want to rewrite it as a fraction. 0.1 is 1/10, so this is 1/10 to the negative x equals 10 to the 2x plus 1. 1/10 is a base 10 number. It's 10 to the negative 1. So now I have like bases again, and I have a power to a power. I'll multiply. I get 10 to the x equals 10 to the 2x plus 1. Set those exponents. Our last example from this set, we have 4 to the x plus 2 equals 10. Remember, when we solve any equation, we need to get the information that has the variable attached to it alone. So first I'll subtract 2 from both sides. Well, 4 is 2 squared, and 8 is 2 cubed. So now I have 2 to the 2x equals 2 to the third. I'll set my exponents equal to each other, and x is 3 over 2. Okay. The second thing that can happen is we can have equations in which the variable is in the base, not the exponent. When that happens, we want to make our exponent on the variable equal 1. And in order to do that, you raise it to its reciprocal. Because when you multiply a number by its reciprocal, you get 1. So we're going to make the exponent on the variable equal to 1 by raising it to its reciprocal. Here's what I mean. Example 1. I have a to the 1/3 equals 4. I need this exponent to become a 1. So I raise a to the 1/3 to the third, the reciprocal of 1/3. Whatever I do to one side, I need to do to the other. So now this, when I do my power to a power rule, this is just a to the first, and that's equal to 64. In example 2, I have n squared divided by n cubed plus 7 equals 9. Well, I can do my division rule, and this is n to the negative 1 plus 7 equals 9. I need to get n alone. I'll subtract 7. N to the negative 1 equals 2. To make negative 1, 1, I raise it to its reciprocal, which is negative 1. What I do to one side, I do to the other. N is 2 to the negative 1, or 1/2. Our final example for this kind of equation is y to the negative third plus 6 equals 14. Again, we need to get y alone. Subtract 6 from both sides. Y to the negative third is 8. I need to raise both sides to the reciprocal of negative 3, which is negative 1/3. So y is 8 to the negative 1/3, which is 1 over 8 to the 1/3, which is 1 over the cubed root of 8, or 1/2. In which we read the sentence to make it exponential. Here's what I mean. In example 1, I have x is the exponent on 4 that gives me 32. So x is the exponent on 4 that gives me 32. Well, I don't know, but we can get like bases now. So 4 is a base 2 number. 2 squared is 4. 32 is a base number. 2 to the 5th. So I have 2 to the 2x equals 2 to the 5th. Set your exponents equal to each other. X is 5/2. In example 2, the exponent on n that gives me 27 is 3/2. N to the 3/2 is 27. 3/2 is the exponent on n that gives me 27. Well, this is the last thing we just saw. We need to multiply this by its reciprocal to get n, the exponent on n, to be 1. So we'll raise this side to the 2/3. What I do to one side, I must do to the other. So n is 27 to the 2/3, which means the cubed root of 27 squared. Cubed root of 27 is 3. 3 squared is 9. In our last sentence style for a logarithmic equation, I have negative 2 is the exponent on 6 that gives me x. Negative 2 is the exponent on 6 that gives me x. And just clean that up. 6 to the negative 2 means 1 over 6 squared, which is 1 over 36. And you're done. So when you see a log equation, don't panic. Read your sentence and go from there. So we'll have more complicated or complex logarithmic equations. In this case, you're going to want to condense your equation using the properties of logs that we learned the other day, and then follow what we did in the simple steps. Read your sentence and go from there. Alright, so let's go see what happens in number 1. In number 1, I have an exponent on a log, and I have two logs separated by addition. They have the same base, so I can, first of all, I think because the exponent's on the number, but they've already been expanded, I'm not going to swing it down front because that would expand it more, and I'm actually trying to condense my logarithm. So instead, I'm going to evaluate that 2 cubed. So I'm going to say that this is log base 2 of 8, 2 cubed is 8, plus log base 2 of 2 squared, which is 4, equals log base 2 of x. Simplify where you can. Now I have 2 logs base 2, separated by addition. I can condense that back into a multiplication problem. So this is log base 2 of 8 times 4, equals log base 2 of x. 8 times 4 is 32. So I have log base 2 of 32 equals log base 2 of x. Just like with our exponentials, I have the same base. I have the exponent on base 2 equals the exponent on base 2. I can drop that and set the other part, the result part, equal to each other. So here, 32 must be x. Okay, let's try another one. In example 2, I have everything is log base 2 again, and they're separated by addition, so I'll condense that to a multiplication problem. X times 8 equals log base 2 of 4. So this is log base 2 of 8x equals log base 2 of 4. Again, since you have exponents on the same base, drop that. 8x equals 4. X is 4/8 or 1/2. Our last example for this section. Here I'm looking for the base, the exponent on what base, and I've got two logs to that same base x separated by subtraction, so that came from or condenses back to division. So I'll condense this side to log base x of 64 divided by 16 equals log base 4 of 16. Well, 64 divided by 16 is 4, so log base x of 4 equals the exponent on 4 that gives me 16 is 2. Oops. And now I can read this sentence. 2 is the exponent on x that gives me 4. Well, if x squared is 4, x is positive or negative 2. Remember, when we solve a square, we square root and we get all possible roots, so it's plus or minus root 4. With all of the previous examples, you did not need a calculator, and I will not let you use a calculator. But in the end, there are some problems in which you need your calculator. For example, it's really when you can't get like bases. So in example 1, I have 2 to the x equals 5. I don't know what exponent on 2 gives me 5. I know that 2 squared is 4. I know that 2 cubed is 8. So it's going to be 2 point something, something between 2 and 3. But I want an exact answer, or a better approximation anyway. So you need to remember that the whole idea of a logarithm came from, it's the inverse of an exponential. When I graph log curves, they're the inverse of my exponential to the same base. So we use inverses to undo things in math, and same thing here. The inverse of an exponential is a log, so to undo a logarithm, or undo an exponential, we log. With my variables and my exponent, I log both sides, because in any equation, what I do to one side, I do to the other, whether it's adding something or subtracting something or logging something. And then we have the rule that says when there's an exponent on a log, we swing that down front. So we're going to swing that variable down front. X times log 2 equals log 5. And then that's multiplication. So to get x alone, we do the inverse of multiplication, which is to divide. So x is equal to the log of 5 divided by log of 2. And that you go straight to your calculator for. A scratch pad or a calculator page, let's grab a fractions template. Our log is base 10, so control log. You don't have to write the 10 in there, it's implied. And we're going to do log 5 divided by log 2, whoops, not base 2. Log base 10 of 2, the exponent on 10 that gives me 2. And I get 2.322 or so. So x is approximately 2.322. Okay, well, e to the 3x equals 5. I don't know the exponent on e, 2.718-ish, that gives me, well, to the 3x, it gives me 5. So again, to undo a variable and an exponent, I'm going to log both sides. You can do common log, but when you see e, natural log is actually better, because the natural log is log base e, and so when I end up getting an exponent on e that gives me e, that whole thing simplifies to 1. Natural log of e is 1. You'll see how that's going to work itself out. So when you see e with an exponent on it, undo it by natural logging. So here I'm going to take the natural log of e to the 3x, and that equals the natural log of 5. I have an exponent on a log, I swing it down front. 3x times the natural log of e equals the natural log of 5. And again, the natural log of e is 1, so this is 3 times x times 1, or 3x equals natural log of 5. Get x alone by dividing by 3. And again, you go to your calculator. Natural log is above e to the x because they're inverses of each other. So control natural log 5 divided by 3. And that is about 0.536. And that is it.